Hey everyone, so this is going to be the last video that I do where I'm going to continue talking about something else with circuits. There is one last thing, some extra parts to this that I need to go over, such as power and Kirchhoff's junction rule, but that's actually going to be saved for a worksheet. So this is going to be the last video for the notes. So before we move on, I just want to try and go over this last question. So pause the video, work itself, and we'll go over in a second. All right, so there's two different ways to do this. Now, I try to avoid using the actual equation. So first, I'm going to actually show you what I do or why I would recommend. So the whole idea is that this line, this is supposed to represent a section of a circuit without a battery. So a battery would be connected across here in order to make the circuit. So even though this looks really weird, this is a parallel connection. These resistors are all on different branches uh, and they are in different loops to a battery. So even though it doesn't look like it at first, that's kind of what's going on. Now, the other thing to mention is the total resistance of a circuit never depends on the battery. It only depends on the resistors and how they're connected. So, regardless of what battery I put this in, these three resistors connected in parallel will always have the same total resistance. What this means is that I can actually make a circuit with a battery, make up a battery, and fill out my VIR chart and use that to find the total resistance. So if I do that, I take my diagram, I do P saw at top. I'm to make my life easier, I'm going to look for a number that all these can divide into. So I'm going to choose 12. So my battery voltage is going to be 12. And then my three resistors are 3, 4, and 12. So then from here, what I'm going to do is everything in this column is the same. So 12, 12, 12. I could do V equals IR and divide the 12 by 3, get 4. 12 by 4 is 3, and 12 by 12 is 1. Add up the currents in this column to get 4 plus 3 plus 1 is 8. And then V equals IR again, 12 divided by 8 to get 1.5 as my total resistance. So again, regardless of what battery voltage you use, you still would have gotten the same value. Now there is a second way to do it, and that's using the actual equation. If you look on the reference table, you'll see that for a parallel circuit, the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So I'll show you once how this equation works. So we're going to plug in 3 ohms for the first, 4 ohms for the second, and 12 ohms for the third. Then what I'm going to do is add these all up. If you want, you can kind of get like bases, but what you'll end up getting is essentially 8 over 12 ohms. Now here's the thing. It's not the total resistance equals this, it's 1 over the total resistance. So after I get to this final answer, I have to flip the 2 points to get that the total resistance is 12 divided by 8, which is 1.5 ohms. This ends up being the reason why a lot of people make mistakes. They always end up forgetting to flip it at the very end, and they end up losing points on the question. So that's kind of why I avoid using it, and I always recommend using the table if you can. Make up a battery because it honestly doesn't matter what the battery voltage value is, as long as you choose an easy one that you can kind of do the division very quickly. All right. So the last thing that I want to talk about is meters. So as you probably may end up seeing when we do some of the circuits and we do a little bit of the hands-on measurements, we have meters that actually help determine and measure voltage and current. So we have a voltmeter which measures voltage. Who would have guessed that the voltmeter measures voltage? Now the thing with the voltmeter is that it has to be connected in parallel. Now remember, parallel means its own separate line. So we have a circuit, we tack it on in parallel on a separate line in order to actually have the voltage read. The other meter that we're going to be using is ammeter. Am for amps measures current. Now the ammeter actually is going to be measured connected in series, and this means that it has to be on the same line as whatever you're going to be measuring. What I usually recommend is that you put the ammeter pretty much right at the end of whatever you're going to measure. If you're going to measure a resistor, you put it at the very end of that resistor. All right. So I'll show you what I mean in a second, but I want to actually do a few questions. So the first one is, what do you think an ohm meter measures? So pause the video, work yourself. I'll go over in a second. Well, if you couldn't guess, ohm meter measures resistance because resistance is measured in ohms. All right, so here's the next question. Pause the video, work yourself, and we'll go over in a second. All right, now here we need to put the resistor and the voltmeter, the voltmeter and the ammeter in the correct spots. Now, as I said before, the voltmeter is always connected in parallel on its own separate line, as in I can either go through a path through the resistors or I can take a detour around them with the voltmeter. So if we look at here with circuit 2, if I go here, I have to go through the voltmeter and also go through these resistors. So this is not connected in parallel. Same thing here. I can bypass this resistor without going through the voltmeter, but if I go through the other resistor, once again, I have to go through that voltmeter. This one's wrong because it's not on its own separate path. Here, again, I have to pass through this voltmeter in order to get to the resistors, so that's not. So one is the only one that's connected properly. The voltmeter, instead of passing through these resistors, I can bypass it and go through the voltmeter, or I can go through the resistor. And then the ammeter is always connected in series in that no matter which path I take, I'm going to go through the ammeter. So the ammeter is going to be measuring the total resistance. The total current through the resistors. All right, here's the next question. Pause the video, work yourself. I'll go over in a second. All right, so for A, they want us to put the ammeter to measure only the current through resistor 1. So if we're only measuring the current through resistor 1, that means it has to be right next to resistor 1. So the answer is 3 because it's right next to resistor 1. I only go through it when I go through resistor 1. Be careful. Be careful if you draw a circuit and you place a meter. Try to avoid putting a meter here because that would be wrong. Because technically it's at what we call a junction. You can go through that meter regardless of what path you take. So try to make sure that there's a space between the meter and the junction. And if you want, you could put it right next to the resistor just to make your life easy. For part B, now we want to find the ammeter to measure total. So since we're looking for total, we're going to say that we're going to want to put it as close to the battery as possible. And that one is this one, 4. Because regardless of what path I take, I always go through 4. And then the last one, where should the voltmeter be? It should be located at 1. Because again, its own separate line. Instead of going around, going through resistor 2, I can go around it like this. All right. So now try drawing it yourself. So you can pause the video, work yourself, and we'll go over in a second. All right. So for circuit that has a battery and 2 resistors connected in parallel, it will look like this. So I draw my circuit. I draw my parallel circuit first, and then the ammeter is measuring the current through 1 resistor. So just like with the previous one, you put the ammeter right next to one of those resistors. It doesn't matter. Again, keeps the space between the ammeter and the junction. And then the voltmeter is going to be attached across the other one. So you basically, after you draw it, you add new lines to go to the voltmeter. That's how you should end up doing this. So I'll sketch it real quick so you can see the method. You just make your little resistor, make your parallel circuit like this, and then again you add the meters later. the ammeter goes here for this one, and then the voltmeter gets attached separately across here. And there you go. Here's the next question. Pause the video, work itself. We'll go over in a second. All right, here we have a series circuit. So again, we start off with drawing our series circuit. So it should look something like this. One single loop. An ammeter is going to measure total. So I'm going to end up putting it right over here, right next to the battery. And then the voltmeter is going to be attached across one of the resistors. So again, across the other resistor, I just make a new path around it, add a little V, and that's my circuit. Of course, you want to label it, but that's what it's going to end up looking like. And then from here, make the chart. This is a series circuit, so we use SASA, put in the voltmeter and the resistance values. So add up the resistor value to get 8, V equals IR. To find the total current is going to be 1.5. So we already know what the ammeter is reading. Everything in that column stays the same. And then V equals IR again, multiply those two to get the voltage to be 4.5 volts and then 7.5 volts. And again, the voltmeter is measuring the voltage across the 5 ohms, so that one's 7.5. And there you go. See, using SASA and PSAW makes filling out the chart extremely quick and easy. All right, here's the last question. So just as a little recap, pause the video, work itself, and we'll go over in a second. All right, so here, again, if we keep adding resistors to a parallel circuit, what ends up happening to the total resistance? Well, it's going to end up decreasing because adding more ends up decreasing the total, and that's going to result in an increase in current. There's an inverse relationship between resistance and current. So if one goes up, the other one has to go down. And as I said, if we use the analogy of cash registers, the more cash registers that are open, the more people that can move through, which means the less resistance there is for people going through. And that's pretty much it. So this is an example of what I meant, where it would be really helpful for you to remember those phrases and those the concepts behind series and parallel and how it relates to total resistance and current. Rather than just focusing on doing the calculations. You could do a question where you just make a very quick parallel circuit with 2 resistors and then a third one, see what happens to the total current and resistance. But again, that would take a lot of time compared to just remembering that parallel circuits keeps decreasing things, or decreasing resistance and increasing current. All right, that's it. If you have any other questions, please let me know. Otherwise, good luck and have a great day.